Welcome to the Memphis Astronomical Society. We are a real thing. We are a 501c3 educational society registered in the state of Tennessee. We are so official we have our own QR code, so feel free to scan that and it'll take you right to a page where you can sign up and join and all kinds of fun stuff. In fact, it'll take you to this page where you can sign up for our newsletter or you can sign up to become a member. Our membership dues are $25 a year. You get the newsletter, you get access to our private dark sky observing site. You get all kinds of features for that measly $25 a year. And even if you're not interested in astronomy and just want to support what we do, join and help us out. Thank you very much. We have a website with a calendar on it, and we try to do things on a calendar basis. This month this coming Saturday, we've got a telescope mentoring session at Hinton Park in Collierville. Those start before it gets dark on purpose, so that if you're new, you've got a telescope you need help with, then you bring it out. We try to get it set up before it gets dark where we can all see what we're doing and work with you to help you learn how to drive your telescope, learn how to become a certified telescope driver. And we go into the evening and do whatever observing we can, and there'll be somebody there to help you out. We have another one. We have a observing. I'm so surprised Mylan's not here. Saturday night we had an observing session downtown off of Bill Street Landing. I didn't go. I was supposed to go. I didn't. I left Mylan on his own to do that all by his lonesome, and I hate that I did that, but my wife was sick. So I don't know how it turned out. Was it any good? Did y'all go?
We didn't make it, but we were wondering the same thing with the haze experience.
The haze was terrible. So we've got another event scheduled for the 28th. This is downtown and the Beale Street Landing. It's an interesting venue. It's not dark. It's not great, but it's a whole different crowd than what we normally see. And a lot of people get interested, and some of the smartest 5- and 6-year-olds have walked up and started telling me stuff about astronomy that even I didn't know. So you'd be always surprised at what you might run into out there. So that's scheduled for this month, and that's about all we've got on the schedule. June's a sparse month. So we have a couple of new members since our last board meeting, Mary Lee Hall and John Hall. Any chance, any of Mary Lee. Broke the chain. Normally people don't show up after they sign up. So.
Not Jim, not John.
Oh, okay. So I got that wrong. We got that wrong. I'm sorry. Merrill, that's Jim Hall, not John Hall. Thank you. So we'll get it fixed. Thank you very much for joining, and hope you enjoy what you get out of it. We have a newsletter. This last month we had an article about our most recent picnic, which we did and had a lot of fun at. There's a lot of pictures in here. I forgot what else is in here. I don't think there's an extraneous article per se. There's an announcement. Well, there's a thing about the meeting tonight, and then an announcement about a former vice president of the Memphis Astronomical Society. In fact, I think he was vice president when I joined in '94. He was vice president for a good number of years back when the vice president's job was the hardest one in the society. We didn't have 2 vice presidents back then. There was only one, and he had all those duties, observing programs, everything. So Hey, Richard.
That was one of the best things we did was split it because it made it a lot easier to get somebody to run.
Yeah, that was a hard time. We actually had years where we didn't have a vice president because the job was so hard. So we finally wised up and made it 2 jobs, and now we're doing a little better keeping vice presidents. Yeah, it is too much. So a number of the older people in the society know and remember Lee well, and I've asked for anecdotes or stories, and hopefully next month we can put something of a memorial to Lee in our newsletter. So rest in peace, Lee. Wednesday the 18th, we've got a astrophotography group meeting. This always happens on Zoom only. You need to be a member to join that, but once you're a member of the Memphis Astronomical Society, you're welcome to join these at any time. Merrill, are we indeed on for this month?
I get my microphone. Yes, and I changed James's name on the roster. We got a fat finger or something here. I don't know.
No worries. Thank you, sir.
We're on for this next Wednesday and get some good stuff going.
Excellent. The great voice from the sky speaks. We have a store. We don't make anything off this store, but if you want some cool stuff that says Memphis Astronomical Society on it, and I didn't make it on my 3D printer, then they have it. Shirts and cups and all kinds of stuff with our logo on it. And then over here I've got little key ring things you're welcome to, and there are those. In fact, Marlon, I have your name tag here in the glow-in-the-dark version for observing sessions.
Did you know about Fred Espinac passing?
No.
Yesterday.
Oh, no.
Yeah.
And he taught where? He taught at
Mr. Eclipse.
Huh?
Mr. Eclipse.
Oh, Mr. Eclipse. Yeah. So another great in astronomy, Fred Espinac was known around the world as Mr. Eclipse. He's written books on observing solar eclipses, taking pictures of solar eclipses, all this stuff. He was the world expert on it, if there was one. Passed away yesterday, apparently. So another little bit of sad news. All right, without further jargon from me, Miss Ann's going to talk to us about SkyNet, and that's okay. It's not the one from the Terminator. This is not your father's.
So my motivation was that I've been teaching astronomy for a long time, and the skies in Memphis have been getting worse and worse and worse. When I first started teaching, we could actually make out constellations, so we had a constellation lab, and now we're lucky if we can see the handle of the Big Dipper and Orion, and that's about it. So it's really hard for me to get students excited about astronomy when we can't really see anything from Memphis. Even with we use 8-inch Schmidt-Cassegrain telescopes, there are very few objects that we can see well in Memphis. So let's see. Here we are. There's Memphis. And so we're right in a very light polluted area. So I wanted to do something different. And so I attended a workshop, part of a physics teaching conference, and I learned about something called SkyNet, this robotic telescope network that has telescopes all over the world that students can log in, use those telescopes, get the data. So I went to this workshop and I learned that there was more to it than that. But as Rick said, it's not this SkyNet, it's this SkyNet. So if you're too young to remember, this is from the Terminator movies back in the 80s. But this network is all over the globe, and they're constantly adding new telescopes. They are all large aperture telescopes. So 14 inches is the smallest they will accept on the network. And they're available to students. And then I learned at this workshop that there were 2 different curriculum sort of packages packages that you could subscribe to. So I thought, well, great, this is worth a try. I don't have to create anything new. I can just use one of these curricula. The first one's called Our Place in Space, and this is for sort of students just learning astronomy. They kind of learn about different distances in the universe. It's kind of a good one. This one is for more advanced students, Multi-Wavelength Universe, and there they're doing more radio astronomy and different wavelengths of the spectrum. This network is also used by researchers in astronomy, but I thought, what the heck, I'll try it. It was only $65 per student, and they get access to the network. They can make their own observations, and they get all this online tooling to help them analyze images and do some of the graphing that was involved in some of the laboratories. Okay, so it was started by Dr. Dan Reichert at the University of North Carolina in Chapel Hill, and he basically had the same problem I had. He'd been teaching astronomy, the skies were getting worse and worse, so he said, I want to make a network so that my students have access to really good telescopes and can do some really good astronomy, and I want my students to do and understand what astronomers do. So what does it mean to be an astronomer? How do you measure the distance to something? How do astronomers do all that? So he created this network, and here he's standing by one of his telescopes at the first observatory that was part of the network, and that was this one at Cerro Tololo, and it's here on the in Chile, a little north of Santiago. And they got a grant from the National Science Foundation to build 5 telescope domes. And I think it's these 5 or 6 here. 1, 2, 3, 4, 5. I think there's one right there. I think there were 6 to start. Now they're up to 8, and they're a couple of different sizes. Most of them are 0.4 meters, but they do have one in this suite here that is a 40-inch telescope. So that's a really big telescope. The network was initially constructed to detect gamma ray bursts, and they were successful within like the first 6 months. One of the students found a gamma ray burst that was one of the most distant ones ever detected. So this is a beautiful observatory. It's way up high in the Andes Mountains, and what's really neat is there's this little video, hopefully. You can watch the telescopes open. So as soon as the sun goes down, telescopes open, and you'll see the telescopes start to slew. If you watch one, they'll start to move a little bit. There they go. And they'll start collecting their data, maybe doing some flats, and before they start running observations at night.
They all pointed at the same thing.
It looks like in this case maybe they did it just for the video.
Yeah.
Okay, so that was the first one. That was around 2005, 2006. Now they have an entire global network of telescopes that is on this SkyNet network. A lot of them are in the eastern part of the United States, the American Public University System, various observatories. Hampton-Sydney College is a small college in rural Virginia. It's about maybe a little smaller than Rhodes, but they have a really nice telescope. My husband actually taught there for a year, so I've seen their telescope. Green Bank Observatory is a radio telescope, and they recently added this one so students can now do radio telescope or collect radio telescope data. So it's really exciting. Then we had a nice talk a few months ago about the Yerkes Observatory in Illinois. They have recently joined the network, which is pretty exciting. There are 3 observatories in Australia that are on the network, a couple in Canada. I think there's a lot of smoke there at this time. And then here's the one in Chile, and then there's also one in Krakow in Poland. And any telescope can be added to the network as long as it's big enough and it can be remotely operated. So my goal is to get the Rhodes College telescope onto the network so other people could use it, or other students could use it while we're not using it, which is actually a lot of the time. It's just sitting idle, and we might have a student one night a week, but there's 6 other nights during the week. All right. So I'll just show you a picture of the other one, and then I'm going to jump over to the actual network. Here's the observatory in Krakow. It's a beautiful observing space, a part of this university, and this is an inside shot of their giant telescope. I'm not sure exactly the specs on this one. We can look it up in a sec, but you can see the dome and how the observatory opens. And then this is the radio telescope that SkyNet operates at Green Bank. They got another NSF grant to refurbish this, which this telescope had been decommissioned in 2006. It was just sitting idle. And Dr. Reichert said, we're going to get that on SkyNet. So he wrote a grant, got the money, they were able to refurbish it, and now it's for SkyNet users. And our students actually did some radio astronomy. It was pretty exciting.
20 meters, not small for a radio.
Okay. I'm going to flip over to the actual network here. So this is the SkyNet telescope network homepage. You get a login, you log into the credentials. We do astronomy right, I like that. But what you can see is that under telescope sites, these are all the different telescopes that I just showed you, and probably a few more have been added. I think I didn't put maybe Sleaford on there or something. But you can check out any one of the sites. We'll go to Cerro Tololo, and they have a live view, so it's dark there now. You can kind of see the telescopes here. And at this particular observatory, it looks like there are 4 of the 7 prompt telescopes are operating successfully tonight. They're all doing observations at the moment, so you can see the observation progress. This is probably a city off in the distance, and then these are the telescopes here. And it tells you the weather is good, the dome is open, what is the system doing, is the camera exposing, this one is moving, getting ready to do an observation. So since it's nighttime for most of these telescopes, because they're a little bit east of here, most of them are going to be up and running. And this tells you what telescopes are at this location. You can click on one of them. I'll click on prompt 7. And is that a little hard to read? I'm sorry about that. Okay. So prompt 7 has an aperture of 0.8 meters, so that's a pretty good size scope. It gives you the focal length, the F ratio. It tells you what filters are available on that telescope, the field of view, the pixel size, and then again what it's doing right now. And let's see. Oh, there's a better view, a little bit better. But it will also show you where the telescope is pointing at the moment. It's right here. I'm not sure what object is there, but somebody has scheduled an observation and they're looking at this particular object right now, collecting data, and probably making some really cool image. Some of the telescopes actually have webcams inside, and I think this one does. Oh no, they have an all-sky camera. So it must be really cloudy in Krakow because this does not look like a clear sky for tonight. So this telescope is probably not going to be used tonight. But you can go to any telescope and see what's happening at that location. You can also look at all the scopes that are operating tonight, and it shows you, some are operating, some are idle, they're not doing anything. It's summertime, so not a lot of students are using the network. Hampton-Sydney College, the weather's good, but it's closed, something's wrong with the camera. So you can one stop and see, well, how many telescopes are operating tonight? Some of them had bad weather. This is the Krakow one. It seems to be locked up, or it's not on the network at the moment. These other ones down below, they're actually observing, making observations. And then down below,
If you got a scheduled time.
we'll talk about that, but great question. So please interrupt me with questions because I just kind of put this together at the last minute, sorry. This is just an all-sky map, and the circles are showing you where the telescopes are pointed right now. And so sometimes you'll see one zoom around as it's slewing to a new location, but it gives you kind of an idea of, what's active tonight, how busy is the network? Maybe will I get my image tonight or will I have to wait a day?
Dr. Viano,
Yeah.
the image of the Yogi Is this an image of the Yogi?
It's probably a real image, but I doubt it was taken by one of the SkyNet telescopes. You need a wide field of view.
The level of quality.
It is a very good image, isn't it? Okay, let's move forward. Okay, we were there, we went to Poland, we went to Green Bay, West Virginia. So here's how it works. If the instructor can adopt the pre-written curriculum, which is what I chose to do, or you could write your own, which is what I would do next time. And then the students are signed up for SkyNet and they get a number of credits. So I think each student in my class got like 5,000 credits. And each observation costs a few credits. So they get enough to do the entire curriculum and some extra to kind of play and have fun as well. And then they learn how to log in. And so for each lab that's coming up the next week, if it requires observations, they have to go to SkyNet and place their observation. And it's super easy to place their observations. And I'll show you how to do that. We'll go through one. And they typically do it a week or two before they need the images. But oftentimes you get your data back in 2 days. But you don't want to wait till the last minute, especially if it's a complicated observation or if it has a number of images. But if you just wanted one picture of Jupiter, you'd probably get it back the same night. But some of them required 14 observations. So we tell them to do it a week or two. Some of them may wait till the last minute and do it the night before. I don't know. But if they don't have the data, we find workarounds. They work with a partner or something. And then when they get their data and they're going through the lab exercise, this is the part that really got me. There is online image analysis software and all kinds of really nice plotting tools for them to complete their lab work. So the course I teach at Rhodes is for non-science majors, and they may not be as adept at using Microsoft Excel to make a graph. Or some of these graphs are complicated. It's not easy to fit a sine wave in Microsoft Excel, but Dr. Reichert has these online tools that make it really easy. So students can focus on the science they're doing rather than struggling with using the tools. I really like that. So we're going to set up our own observation tonight. So I'm going to go back to the SkyNet network here. And so I'm going to choose optical observing, and this lists all the observations that I have done. So most of them are completed. There's none active. They're all completed. But I'm going to show you how easy it is to set up an observation. So you would just say, add new observation. Ta-da! And then you're greeted with a map of the sky. But basically what you want to do is enter the keyword. So what would be a good object? Let's say M3. Messier 3, and you just say search, and it will bring it up. There it is, and it also gives you an image from the Digital Sky Survey, kind of a preview image. So this is a beautiful globular cluster. We'll see if we can set up an observation. So what I would do is pick any one of the telescope sites. I'll just pick Cerro Tololo because there are more telescopes there than any other site. And I would see, if I went back in time, the sun is still up, but here's my object, the red circle. So this tells me my object is far away, and when the sun is setting, my object of interest is just rising. So this is a great object to observe tonight. So I might go ahead, and there's my object. Okay. There are lots of things I can see on this map, but basically I just want to see that my object is visible, it's above the horizon, looks like it's going to be a good one. And then I scroll down to the bottom, and there are tons of options here. It will fill in the right ascension and declination of your object, but then you get all these different options to play with. So how high do you want the sun to be, or how low do you want the sun to be in order to do your observation? So if you're a professional astronomer, you'd want the sun to be well below the horizon. But for students in this class, most of the observations we usually would say, minus 12 is good enough. So we can actually do a lot of our observations before the professional astronomers use the network. And then how high do you want the target to be? If you're a professional astronomer, you want it up pretty high. But for my students, 20 degrees was good enough. So we'll set it for 20. How bright do you want the moon to be? What's your allowable moon phase? For this one, the moon wasn't anywhere near M3, so I can leave it at 100, and if I'm setting it tonight, maybe I'll get it the next day. It's only a quarter moon, so we're okay. And then how far away from the moon? So there are lots of options. There are more options that I'm not going to go through, the advanced settings. But then it generates this graph, and this graph tells me when my object is above the horizon at these different sites. So this purple line says that at Sleaford, which is either in Canada or Australia, I can't remember, it's well above the horizon for at least 2 hours. So if I only need a couple of images, that's probably fine. So all of these different observatories and telescopes, I have a really good shot of getting a good image of M3 because it's up in the sky at several different sites. So then I get really excited and I say, okay, well, what telescopes do I want to use? So I can choose all of the ones that are available, or I can choose just a subset. If I want a really good image, I might pick the best 3 telescopes and see which one I get. But since we're just doing an example here, I'm going to select them all. So I'll select that one.
Is it just going to give you a picture from one?
You'll just get however many exposures you'll set. You can set it to do all your exposures from the same telescope, or just do whatever becomes available. Now, the prompt telescopes, these are the ones that are managed by the University of North Carolina, so they're always in really good shape. They're working well, so I always like it when I can select some of those. What else we have? Australia. That's another prompt scope, so it's run by the University of North Carolina. This one I know wasn't working tonight, but we'll just select them all. So I'll save and continue. And then I get to decide, well, what kind of filters do I want? And as I choose filters, I may lose some telescopes. If that telescope doesn't have a certain filter that I want, it'll disappear from the list. We can do red, green, blue. We could do just a black and white image, high through. It's totally up to the user. I'll just pick high through. But you could select RGB and maybe do one of each, and then there's a way to combine them and get a color image, which I'll talk about at the end.
What is high through?
High through is just like luminance, just lets everything through.
Gotcha.
And then I'll say save and continue. And then it wants to know, okay, how many exposures do you want? Do you want 1, or do you want 10, or do you want 100? Each one's going to cost you some credits, though. How long do you want the exposure to be? And then you have to decide, and that's a little bit tricky. I'll just do 1 exposure. Any guesses? What should I use for M3? 10 seconds? All right. We'll see if we get anything.
Maybe more.
My problem is I never expose long enough. So. But we'll see what we get.
Well, 300 is 10 minutes.
Oh, this is seconds, though.
Yeah.
So then I have 2 different accounts. I'm going to use the one, I have 10,000 credits on the class account, so I'll use that one. And it tells me here that my 10-second exposure is going to cost 10 credits. So not a lot. I might bump it up to 15. So then when I'm ready and I agree, okay, 10 credits is fine, there, I change it to 15. Seems to be about a credit a second. I'll say save and continue. And then you just sort of double check all of your settings so that students don't make the wrong observation. You just double check everything, and then you just say submit. And now it's in my list of observations, but it's listed as active. So if I come back later tonight, it might be completed and I could look at my image. It might be tomorrow night, it might be the next night, but it'll probably be pretty quick since there were so many telescopes available. Did you have a question?
Yes, I did. What happens when you run out of credits?
You would have to buy more credits. But the students in my class get enough to do the entire semester and a bunch of extra ones to kind of play around if they want to do some really cool deep sky photography or something.
And can the students buy over what is allowed?
I think they could, and there is a way to add credits. We didn't have to do that in class. We had plenty of credits, and I still have 10,000 left over. So I actually took back all the credits my students didn't use so that I have 10,000.
Smart teacher.
Okay, so we learned how to set this up. It's really straightforward. And so for each lab, students are told what objects they need to observe and maybe what's the best filter and exposure time. And they go and they set it up and they get their own data. So it really gives them a sense of ownership that what they're doing is their own data, just like a real astronomer. That's one of the great things about it. So this is one, same object, but I had set up an R and a G and a B, red, green, and blue. And so I did 60 seconds each. It would have cost 87 credits to do that. Now, so students get really excited, oh, I'm going to get these beautiful images. They first have to learn what is a good image and what is a bad image. And so in the first lab, they're given a bunch of examples of what can go wrong. I mean, these are serious research grade instruments and things don't always work right. So up here, and these are not calibrated. Some of these images have not been calibrated yet. But every image you get back on SkyNet has been calibrated for you, which is wonderful. Yeah.
Calibrated.
It means that they kind of subtract some features of the telescope that cause distortions. So it kind of makes it look better. Like you can see these circles here, that's just because it hasn't been calibrated.
Are they able to have color?
Yes, we'll get to that at the end. Most of the labs require just black and white images because students are not interested in making beautiful pictures, which a lot of us are interested in that. They're actually going to do science with the image. So a black and white image is fine for what they're going to do. They're going to make a measurement on the image or something. They don't need a beautiful color image. So these are just examples of bad images. And if a student sees one of these artifacts in their image, they have to go reset the observation and get better data before the lab that needs that data. So they really should set it up 2 weeks in advance. So here we have examples of clouds covering part of the image. This looks like a tracking problem of the telescope. This is a focus problem of the telescope. This is actually wind vibrating the mount during the exposure. And the observatory at Tololo is high in the mountains. It's very windy, so sometimes they have wind artifacts. This is somebody left a light on near the observatory. This has a satellite trail through it, and it might not mess up your, what data you need, but you might want to recollect. This is an airplane going through the image.
I thought that right there was a ray of light from the sun.
No, that would make it much brighter, like something like this over here. These are shutter problems, so the shutter didn't quite open and close properly, so you get some artifacts. Can you guess what this one might be? What does this shadow look like? It's a bug actually on the camera sensor or nearby, and so you actually have a bug in your telescope. So you don't want that in your image. You got to go back and redo that observation. Okay, so the students aren't left flying blind. Oh, question, yeah.
So if something like that happens, where it's not something that you necessarily did, but something's kind of there, do they give you the credit for that?
No, but that's why you get so many credits that if you have problems, it's okay. And I know Dr. Reichert would, if he ran out of credits, it's no problem. The instructor and the lab TA get extra bonus credits that they can dole out to the students if something happens. But I didn't have any student run out of credits. So they're not flying blind. They're given information in the labs to help them set up good observation. So, what kind of filter to use, what exposure duration is good for the objects. And here's a sample of one of the students' images of this. This is a galaxy, Centaurus A. So a student took this image in class, and that belonged to him. He's like, this is my image. I'm going to send it home to mom. She's going to put it on the refrigerator. This is my galaxy. So they get really excited. Even though they're not beautiful color images, these are their images. So they have ownership. Okay, there's also a way to image the moon, and I won't go through this on SkyNet, it takes a little bit longer, but when you're setting up your observation, you can zoom in on the moon, and you can actually select what field of view on the moon you'd like to take a picture of. So I set this one up. well, I don't know if this matches this, but the students in part of the introduction lab where they're just learning how to take pictures, they learn how to select a field of view on the moon, and then they get back their picture. And for a student to get an image like this, they're super excited, right? Because I can see craters, Yes, we could do that with a telescope out on our observing deck, but they feel like they're a real astronomer when they've set up the observation, and the telescope they use is in Australia, and they get this beautiful image back. So it's pretty exciting. Okay, I'm going to flip back here, and I'm going to show you. So let's say, we don't have our data yet, but we'll look at another one. So how do you check your images? Well, you would just come down to the observation of interest. Maybe this one.
You set your field of view for the moon on any of the telescopes?
Think so. The instructions tell you to use like a generic 16-inch, which is sort of the average of all, and set that. But I think if it were to use a different scope, you'd then have a different field of view. So you're basically setting the center of the field of view.
You set what part of the sensor of the canvas?
Yes.
That you use.
Yes.
Not swapping lenses on the...
No. If it was a different telescope, your field of view might be bigger or smaller. But So you would just click on the observation, and for this one, it looks like I did 14 images. But you just click on the image. Oh, see, I never expose long enough. This is my problem. So I didn't have good data in this case, so I would have to redo my observation. Maybe we can find a better one. We'll do a planet here. This was the first one I did at the workshop. We did 2 images of Jupiter, and they came back within an hour. It was amazing. And so there's Jupiter.
Oh, wow.
And so you get that, and you're like, yay, I could make a measurement and measure the angular size of Jupiter or something. And then we're going to see how you can adjust that image to bring out the moons, and the students actually do an entire lab on the orbit of Jupiter's moons. So it's really easy to check your data and see, how your data is going. That's still active. Okay. Okay. So in the first lab, they're just learning how to take pictures. So I showed you how you set up an observation, how to check their images. They make some measurements because they're trying to do things that astronomers do. So they learn how to display the image with this online software. It's called Afterglow. They learn how to make plots and make measurements. They learn how to mark things on their image. So here's an example of, it says Pluto here, but it's marked, and they have to identify things. And they learn how to compare images to the digital sky survey so that they can pick out things like dwarf planets or asteroids. Yes?
How do you measure the distance between stars?
We are going to talk about that. I'm so glad you asked, because that's one of the labs that they do. It's not an easy measurement. We use what's called parallax, which is a cool measurement, and it's a way to measure the distance to nearby stars. Okay, so I wanted to show you the image analysis software, and I'll show you how we alter the display, how we can make a measurement, how we can use markers and do maybe a DSS comparison. Okay. So the software that we use to analyze the images is called Afterglow. And you just bring up this interface. It's all included, one-stop shopping, right? If you subscribe to SkyNet, you get access to this online image processing software. And we'll open an image. I'll go to My User Observations. We'll look at Jupiter. Oh, they're alphabetical here. And so once you open it, I know it's kind of hard to see, but you have master calibration images. You have the raw data, which is what we were looking at just to check and see if the image is good. And then you have the reduced images, which have all been calibrated for you, which is really nice. So I have a couple of images of Jupiter. We'll just open one. So there's my picture of Jupiter, and now I can see a couple of the moons, but it doesn't look very good. It's really blurry, and students think it's going to look like the Hubble's pictures. Well, we have to tell them no, astronomers don't get pictures like that most of the time. But they give you a lot of tools here to play around with, like contrast and things. So there I can, so there's my nice planet. So I could actually measure the diameter of Jupiter if I wanted to, and I would get the measurement in angular measurement, it'd be in arc seconds. But if I wanted to, yeah, maybe you can mute everyone. If I want to enhance the moons, then I could measure the distance from Jupiter to one of the moons. But that requires I have to know which moon is which. So in this lab, students will use online software, or not online, but they'll use like Stellarium they'll type in the exact date and time of the image, and they'll be able to identify which moon is which. So that's one of the first things they learn to do, is to use markers to identify. So they would bring up Stellarium, they would type in the date, and all that information is given to them here in the info, the date and time of the observation. But they do learn something important here. These times are in universal time. I know it's hard to see, but it says GMT, so they have to learn how to convert that to put it into Stellarium. Or it turns out you can set Stellarium to work in universal time too. But that takes a little getting used to. But let's say they do that, and so they've figured out that maybe this is Europa over here, and they want to label it in their image. So there's a nice tool here called custom markers. This is all built in, which makes it really easy for students. They just click on it, and then they click on the marker, and they can type it in. And it will label it for them. I think they can move it if they want, but there you can label the moons. So they can get things labeled, they can make it look really cool, they can send it home to mom and dad, it's like, oh wow, our tuition dollars are doing good. So that's one thing that they can do. They learn how to do this kind of thing. Another thing, as we'll see in the next lab, but I'll show you now so I don't have to go back, is they make measurements. And that is the plotting tool. And it's so easy to use. You just click and drag, and it makes a line. And you scroll down, and it tells you how long the line is. It tells you in pixels, but it also gives you the angular measurement in arc seconds, or this one also in arc minutes.
Oh, good.
It's very nice. And so they need that angular measurement to do some important things in the lab. It will also allow you, it will automatically select the center of a bright object. So I just click and it automatically, well, not that one. Let me click planet centroiding. Maybe I can. So I would click there and it automatically picks the center. And then I just go there and it automatically goes to the center of the object. And you can see this is how bright it is versus distance. This is the planet itself starting from the center going out, and then it's dark, 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 dark. And then here's the little moon. You can see we're at the top of the peak. So they make a measurement. It was 85 arc seconds to this particular moon at this particular time on this particular day.
With that much information, you can figure out how many miles it is.
Yeah, you can do a lot of different things. And then another thing, I'll just show you quickly if I can. I don't have Pluto. I'm going to go into one of my students' folders. So this is all the images that Anas took over the course of the semester. And I'll pick a picture of Pluto. It takes a few seconds to load some of these images. Okay, so Pluto is somewhere in this picture. How is the student going to figure out which one is Pluto? So this is an important task that astronomers have to do. When someone discovers an asteroid or a comet or a new dwarf planet, they have to be able to find it in a field of stars. Question? No?
Wait. Can't you just figure out which one is the biggest? Because Pluto is the closest to us, so it should be bigger.
But Pluto is not giving off any light, so it doesn't show up particularly bright in an image.
Oh, so it would be one of the dimmer.
Yes, but you don't know which one. So how are students going to do that? Students been told you have to identify Pluto in this image. It's very simple. This system makes it so easy. You import the digital sky survey, and we can split it left and right. So on the left is the student's image, and on the right is the digital sky survey. So these are stars, no planets, and you have to figure out which one is in here but not in here. And it's not that hard. It takes them maybe a few minutes, but they usually use markers. And they'll start marking stars that are in both, right? So that one, maybe that one. I'm not sure these are. So I was able to find Pluto earlier today. It should be near the center of the image. And, bingo, there it is. So I see 2 stars here, 2 stars here.
There you go.
There's Pluto. So then they can label it, they get all excited. And the labels are really nice. Not this one. Oh, yeah. Click on the marker. You can make it bigger if you want. And then you can label it. I found Pluto. You can change, how far away it is, but you can do all kinds of things. Change the font size and everything. So they can make a nice kind of print quality image with their data. Okay. Any questions so far? I know it's a lot. Okay. So there's ways to set the display so that you can see what you're looking at. You can do plotting, you can set markers, you can compare it to the sky survey, and you can find asteroid. They do one where they find an asteroid, and that's a little bit challenging, but it can be done. Okay, so the first real lab where they're trying to do something like astronomers, it's lab 3, but they observe a planet and one of its moons for 14 nights. So they have to set up an observation that repeats for 14 observations. And they measure the position of the moon from its planet. So if they're doing Jupiter, they'll pick one of the moons, maybe they pick Europa, and they'll measure the distance from Jupiter to Europa on 14 different observations. And it goes pretty quickly. With the plotting tool, you draw the line, you get the number, you put it in your data table. Then they plot the position versus time, and they figure out the period, how long it takes that moon to orbit the planet. They can also figure out the size of the orbit. And they do that with these awesome online graphing tools that I'm going to show you here in a minute. But they can do any of the outer planets. Neptune is a little bit challenging, but luckily the only moon you can see is its biggest one, so that makes it easy. You don't have to identify it. Uranus I find really difficult because there's so many moons. Saturn and Jupiter aren't too difficult. And a lot of students chose Saturn just because they like Saturn. So I'm going to show you these awesome tools. Do this one. So Dr. Reichert has developed these tools because he doesn't want students to spend time figuring out how to plot something. That's not super exciting when you're trying to learn astronomy. And so the tool for this particular lab is called Moon. And so here we have some sample data. So they did about 14 nights, but gee, maybe they're missing a few. They got some data here on like day 2 and maybe 4, but there's some gaps where maybe it was cloudy and they didn't get an observation. So it's really hard to see what the curve looks like. So this has a built-in model, and the students just have to mess around with the model. First they increase the amplitude. So we want the purple curve to match the blue dots. We didn't do a very good job. And what this is plotting is distance from the planet, so how far away is the moon, either left or right. They're all positive numbers. And this is plotting day, so which observation. So the moon was here, and then it was a little farther away, and then it was a little bit closer, and then it was much closer, and then it was far away. So lots of variables here. And they can play around with the spacing. They can shift the phase. I'm not doing a very good job on this one. But there should be a way. You also can play with the tilt. So you don't know if the moon's orbit is, right perpendicular to the field of view, or is it tilted a little bit, and that will affect the bottom end of the graph. And so their goal is to try and make this match. Oh. No. It would help if I knew which moon this was. I think we're getting close. And they can fine-tune it. They'll spend a lot of time trying to get it as close as they can. But you really don't have to be super close to get a good idea of what the period is. So they will fit the curve, and then they can read off the number. The period for this moon was 6.4 days. So yay, they're excited. 6.4 days. And the size of the orbit, they can read off the y-axis. They can figure out how many arc seconds it is.
Well,
question?
there was one time that it was way off.
Yeah, I didn't do a really good job, but here's what a student would do, right? They would get a beautiful fit, where every dot matches up. And from that fitting tool, they can determine the period of this moon, and this happened to be Saturn's moon Titan. The period was about 16 days, and the size of the orbit was 195 arc seconds. So here's what their data looked like. Here's Titan way over here. That's the easiest one to follow. It's the brightest moon, so it's pretty easy for them to follow it from image to image. Now they're not done yet. They have a little bit more work to do, but the goal here is to calculate the mass of the planet Saturn. That sounds pretty cool. I'm going to calculate the mass of the planet. There is a form of Kepler's third law that allows you to do this. If you use the right units, the mass of the planet is equal to the cube of the size of the orbit divided by the square of the period. The period has to be in years, but if you get it in days, that's a really easy conversion. The size of the orbit has to be in astronomical units. They've got it in arc seconds. So they have to think through, well, how would an astronomer make this conversion? And the way it's explained in the lab is really simple geometry. They just do ratios. They say that, see, there's two of these. The angle that they measure is this angle. Well, that angle is to 360 as this distance is to the circumference of this big circle. And the circumference of the big circle is just 2 pi times r. R is the distance to the planet. And that they can look up from Stellarium. And so they're able to convert arc seconds into astronomical units pretty easily. And then they calculate the mass of Saturn. And when you use this equation, it comes out in units of mass of the sun. So you get 0.00029 solar masses, which doesn't really mean much. But then they convert it into Earth masses, and they find out that Saturn's about 100 times as massive as the Earth. And this is actual student data, and this is right on. That's exactly what it's supposed to be. Yes?
Saturn is heavier, but it's less dense.
Correct.
It is the least dense. If you had an ocean big enough, it would float.
Amazing. So a lot of the rest of this course has to do with distances in astronomy. This curriculum was our place in space. So it's about how do we measure how far away things are, how do we measure the distribution of mass in the universe. So we started on Earth, we did some cool stuff with planets, but then they start measuring distances to asteroids and stars. That's what you were asking about. They use a parallax measurement. Stellar parallax for stars. And then as you get farther away, there isn't enough measurement in parallax, so you need a different technique. And this triangle diagram just shows astronomers the different techniques they use to measure distances to objects that are farther and farther away. So once you can't use stellar parallax anymore, you can use a certain type of star that blinks with a certain period, and then you know something about that star, and there's a way to calculate the distance. You can do the same with another type of star that blinks. If you can measure something about that star, you can back out the distance. Same thing with supernova. There's something about supernova of certain type, and we're going to talk about each of these, that you can back out the distance.
Isn't Betelgeuse going to supernova soon?
It might. It could have already happened. We wouldn't know yet.
I mean, yeah, because light years, it probably did happen.
I don't know. You're preaching to the choir here. And then finally, Hubble's law is a way to infer the distances of the most distant galaxies. They don't use the law to measure distances, but they actually determine the Hubble law, or the Hubble constant, which is kind of fun. Okay, so parallax, I'll try and, is it really 8? Okay, I'll go faster. So parallax is a measurement that you probably have heard of, but you can easily do this if you just hold your thumb like in front of the clock or some object on the wall and close one eye and cover an object with your thumb, and then open that eye and close the other one. And now your thumb is in a different position. And if you go back and forth, it appears like your thumb is moving against the wall. So we use that technique. That's called parallax. We use that for a star that's nearby, closer than the other stars. As the Earth goes around in its orbit, its position appears to move against the fixed stars. So in January, it looks like it's over here, and 6 months later in July, now it's way over here. So it's moving back and forth, and students can measure that angle, that parallax angle. And if you know the parallax angle, you can back out the distance. You can also do it to something much closer and just use 2 different observation points on Earth. So now this is the Earth, and if I make a measurement on this side and a measurement on this side, I will measure a parallax angle for some object against the background sky. And our students do this for an asteroid, and they measure the distance to an asteroid, which is really cool. And then they do it for a star, Alpha Centauri, our nearest star. So here's the student image for the asteroid Hilaritas, which they called hilarious, but it's Hilaritas. So again, they had to use the Deep Sky Network to identify the asteroid, and then they had to do multiple observations from different locations on Earth, so they would get this baseline, and they learned how to stack 2 images together. So another one of the tools in Afterglow is a stacking tool. And these were probably 2 images taken from different telescopes. So in one, the asteroid is really bright, and in the other, it's not so bright. But remember, the plotting tool will automatically find the center of a bright blob. So it doesn't matter that they're different. So they measure that parallax angle, and then through a little bit of geometry, they can back out the distance, which is pretty exciting for them. They find the asteroids really are in the asteroid belt. You know, who knew? It was pretty exciting. Okay, the next thing to measure distances are things that are farther away than our solar system, farther away than the nearest stars. You need something brighter so that it is visible farther away. And variable stars are pretty bright objects. This is a graph showing the brightness versus something called the pulsation period. There are stars that are in a certain phase of their life that they're actually blinking on and off, and they're called variable stars. And there are kind of 2 types. There are our Lyrae stars, which aren't especially bright, but they all have about the same brightness. And then the Cepheids have varying brightnesses depending on their pulsation rate. So the Cepheids will blink on and off anywhere between 1 to 100 days. But if you can measure that pulsation period, you can get something called absolute magnitude, which is really just how bright the star is, how much energy is coming out of the star. We just put it on a scale called magnitude, because it's like apparent magnitude, but this one's absolute because it relates to the actual energy coming out of the star. So if you can get this absolute magnitude, or you can think of it as just energy coming out of the star, And if you know the apparent magnitude of the star, which is a relatively easy measurement, apparent magnitude is just how bright does it appear to be, and we have a scale for that. If you can get those two numbers, you can calculate the distance. So the goal in this part of the course is that they look for objects that have these special kind of variable stars, and they measure the pulsation rate, and then they can get the absolute magnitude, and then they can back out the distance.
And measure the temperature of the star based on the magnitude of the light.
To measure the temperature, you would need to plot the star's light as a function of frequency, and then you would find the peak, and that would give you the temperature. They don't do spectroscopy like that in this course, which is the one thing I wish they did do. Maybe the other course has it, or I would write my own to do that. There are other objects that have known luminosities or known brightnesses, which means you can use this equation. And supernova are one of those objects. There are actually two types of supernova, but type 1, this blue curve, is always the same for every type 1a supernova, or type 1 in this case. It always reaches a maximum at this level, and it always has the same absolute magnitude, so this number. So if you can identify that the thing you're seeing is in fact a supernova of type 1, then you can pluck off its absolute magnitude and use this equation to back out the distance. Yeah, I think I put it in here. So for RR Lyrae stars, if its period of pulsation is less than 1 day, then you know you have an RR Lyrae star. And you're like, okay, I'm home free. It's one of these stars. Its absolute magnitude is 0.75. Boom, I can back that out. If it's a Cepheid, well, it's a straight line. You could use the graph. You know, if it's 20 days, you could go up here and try to get the number, but that's a little bit hard. There's actually an equation to do that. It's not a complicated one. This is a log scale, so it would be hard to actually do it just by eye. But it's a simple equation that they can calculate it. If it's a type 1a supernova, it always has an absolute magnitude of minus 19.3. So if you can identify which object do I have, then you either know the absolute magnitude or you can calculate it, then boom, you can get the distance. And so what kind of things do they do? The first one, they look at globular clusters in our Milky Way galaxy. And globular clusters kind of are a bubble around the Milky Way galaxy. So if you can measure the distance to a lot of these, you could kind of map the size of the Milky Way. And that becomes important for a later lab. So here's an example of NGC 1261. It's a beautiful globular cluster. Now, in order to do this, you have to know which star is blinking, and so they're given that information. And you have to have the apparent magnitude of some reference star, and they're given that information in the lab. But they have to go in and identify these two stars. It's hard to see in this one, but you can zoom in and afterglow, and you could pick on those two stars. And there's another tool called batch photometry, which will go through a series of images of this globular cluster, and it will measure the brightness of these stars, and it will help you make a graph of the brightness of your variable star versus time. And so you can see that it's pulsing, bright, dim, bright, dim, bright. And from this, they can measure how long what's the period of the pulsation from bright to bright. And it's about, half a day, 0.4 days. So that tells them it's an RR Lyrae star. It's less than 1 day. So, yay, I found an RR Lyrae star. Now I automatically know the absolute magnitude. I can calculate the distance. And this batch photometry process also gives you the apparent magnitude of your star. So you get both M's, quick calculation. You can get the distance to this star, which is associated with this globular cluster. So you've got the distance to a cluster. Then for Cepheids, it's very similar, but in this one we're looking not at things in our Milky Way, we're looking at other galaxies. So far away objects. Cepheids are incredibly bright. So you can see them when they're really, really far away in a distant galaxy. And so you kind of do the same thing. You find the galaxy, you take a series of pictures. You're told what is the reference star and what is the Cepheid variable star. And the tool helps you plot this light curve. I won't go through the tool, but if you want to see how it works, I can show you afterward. It's actually pretty cool. But you get this light curve. You can measure the period. And then on this previous slide, 2 slides ago, if it's a Cepheid variable and I measure the period, I can calculate the absolute magnitude. And once I have the absolute magnitude, I can calculate the distance. So the student did this for this particular galaxy, and it turned out to be 504 kiloparsecs away. And a kiloparsec is about 3,200 light years. So it's pretty far away. So this is a really great lab for students because this idea of finding objects with known brightness and using that to back out the distance is something that's really important in astronomy. And here they get to do it on their own data, and they get these beautiful graphs. I don't know that my non-science majors appreciate these beautiful graphs, but they get the data and they're able to make these calculations. All right. Any questions about this? Yeah, let's go back there. Oh, Cooper, hello.
The pulsation rate, how can you distinguish that between like the twinkling of stars that you see at night, especially if they're low to the horizon where they experience a lot of twinkling?
Good question. Cepheids are very regular in their pulsation. And if it's between 1 and 100 days, then you've got a Cepheid. And it's going to be a bright object in a very distant galaxy. That's usually how we do it. But twinkling of stars, nearby stars, is just atmospheric effects. And if you're observing for, this was an observation that took 130 days, so you wouldn't see twinkling every night. So if you got this curve, you're like, I've got a Cepheid variable. Plus, in this lab, the students are told, hint, it's a Cepheid variable, and then they're led through this to calculate the period. Yeah, you had a question.
How are you able to do short-term predictions for star systems that have the three-body problem?
Short-term predictions for star systems that have 3 objects?
Three-body problem.
The three-body problem is when 3 different objects.
So like the Sun, the Earth, and Jupiter. 3 objects.
No, 3 stars.
3 stars.
Similar mass.
So Newton's laws are very powerful, and you could actually calculate that, maybe not analytically, so using equations, but you could use numerical methods probably to solve that. That's not what I do. I'm not that kind of an astronomer. I'm actually not an astronomer at all. I'm an amateur astronomer. But I think it could be done just based on Newton's laws.
Or you could watch the TV show.
Or you could watch that cool TV show. I watched that. I really enjoyed that.
You mean Star Trek?
Three-body problem.
Three-body problem.
Okay, so the last one, they use these techniques that they just learned to map the Milky Way. And this goes back to the early 20th century where there was this great debate, right? Where is the sun in the Milky Way? Where is the Milky Way in the universe? Nobody knew at this time. Shapley and Curtis were kind of debating. I think, now I'm going to forget, I had practiced this. One of these people thought that the sun was in the center of the Milky Way. The other said, no, it's not in the center of the Milky Way. One thought that the Milky Way was fairly small. The other thought that it was 10 times bigger. And then nobody was really sure about how big the Milky Way was compared to other, what they then called spiral nebulae, but those were other galaxies. Like the Andromeda Galaxy, right? It looks fuzzy, and they called it spiral nebulae, but no one was really sure how did they compare in size to the Milky Way. So our students do an experiment where they do exactly what I just showed you. They use globular clusters. They find RR Lyrae stars. They measure the pulsation rate. Yay, it's an RR Lyrae star. I know its absolute magnitude. I can calculate the distance. And they do that for all these orange dots are different globular clusters. And they do it for different coordinates in X and Y based on our location here, the sun. And then they plot those on this 2D axis, and they're basically mapping the Milky Way. So each orange dot is a globular cluster, and the yellow one is the sun. And now they get a map of how big the Milky Way is, and where is the sun relative to the center. So if you imagine kind of drawing a circle here, the center is going to be over here. So the sun is not in the center of the Milky Way. And then they can measure the distance in kiloparsecs, either way, or take an average, and they can find out that the Milky Way is roughly 30-ish kiloparsecs in diameter.
AI says Shapley's the one that got it right.
Yes.
Okay, I couldn't remember. They were both presented in the lab, and I just couldn't remember who was right. One got it right for the first 2 points, the other got it right for the last point. So that's really exciting, but what about this last point? How does the Milky Way compare in size to these other galaxies? So our students then measure other galaxies. This is a spiral galaxy, and yeah, it's blurry and all, but you can measure the diameter, and you can convert that into kiloparsecs. And they find that, the Milky Way is about the same size as all these other galaxies. So the Milky Way is not the entire universe. The Milky Way is one of many galaxies in the universe. Okay. We're almost there. The last lab using the system was the Hubble law. And the Hubble law looks at distant galaxies, and it's usually presented as a graph where you plot distance from, say, Milky Way to the distant galaxy. And this is put in millions of parsecs now, megaparsecs. And on the y-axis you plot the velocity of that galaxy. So how fast that galaxy is moving away from us. So one of Hubble's great discoveries was that every galaxy he looked at was moving away from us. And he plotted it on this graph, and he found out that the farther away it is, the faster it's moving away from us. So it's kind of like, you've been in here a while, you've been listening to me, you're tired of hearing me talk. Those of you who are far away could turn around and run pretty fast, and I wouldn't notice. But those of you who are close, you would slowly sneak out, and then as you got closer to the back, you would just speed up. So the farther away you are, the faster you're going away. That's the Hubble law. So our students make some measurements, and they are able to make this graph. So what do? Well, they go to their CFID variables again in distant galaxies. They use just 5 distant galaxies. They find the CFID variable. They're actually told this star is the CFID variable. They plot the light curve. They get the pulsation period. And then they're able to measure the distance to that CFID variable. Or they get the distance to that galaxy. And then to get the velocity, that's a little bit trickier. This is where they get to use radio astronomy. So they actually measure the spectra, or they measure the position of the 21 centimeter hydrogen line. That is a line due to the emission of hydrogen, and it will be shifted based on how far away a galaxy is. That's the redshift of the galaxy. So this one, they get to use the Green Bank radio telescope, and it's a really cool idea how this works. Because these lines are really dim, these galaxies are far away, and the radio signal coming from the hydrogen that's giving off this line is not very strong. The radio telescope does something really clever. It will take a spectra, so there are 2 graphs here, frequency on the x-axis and just radio power on the y-axis. There are 2 just because it's doing it in 2 directions on the radio dish. But it's measuring across the frequencies, and it's telling how much radio signal it gets. These 2 blips here, that's hydrogen gas in the Milky Way. It's a very bright signal, and when you're looking out, you're going to be looking through parts of the Milky Way. The radio signal due to this galaxy, this is M83, is buried here. You can't even see it. It's so dim. So what the radio telescope does is it takes one spectrum pointed at the distant galaxy, and then it moves away and it takes another spectrum. So here you can see the Milky Way's hydrogen lines, but now the ones due to the galaxy are gone. Trust me, they're gone. I know you can't tell. But then it will subtract these two, and you'll look at the difference, and then those two lines pop up, or the line pops up. It actually is a broad line, and it kind of looks like two peaks, but the broadness is because the galaxy is rotating, so some of the galaxy is moving away from you, and some of it is moving towards you. You get a little bit of Doppler shift, in addition to the Doppler shift due to the galaxy moving away from you. So the line is kind of broad, but we just go for the center, and that is the hydrogen 21 centimeter frequency. You can turn it into wavelengths. But from that wavelength and how far it's shifted from nearby hydrogen, that tells us how fast the galaxy is moving away. That's the Doppler shift. It's a simple calculation, and they can get the velocity. So CFIDs to get the distance, radio astronomy and the Doppler shift to get the velocity. They can plot the Hubble law, and they can get the slope of this graph, which is the Hubble constant. Yes?
Two questions. One, you said everything's moving away from us. So I'm assuming we're moving away from something. So where is everything moving away from?
There is no center to the universe.
Everything's moving away from everything.
Well, so within a galaxy cluster, galaxies are gravitationally bound, so they're not necessarily pulling away. But between galaxy clusters, space itself is stretching. So it appears that everything is moving away from everything else. It's a really strange concept. I hope we can do a talk about that and bring someone in who can explain it, because cosmology is... You had a second question, yeah.
You said the things that are farther from us are moving faster away from us. Why is that?
Because that's what Hubble found. Oh. That's why.
And we're still trying to explain.
You can think about it if you took a piece of spandex and you were stretching it, and you put a marble, at some point, the farther it got, the faster that material stretches. And it's just the nature of spandex. People have done studies on spandex, and it follows the laws of gravity pretty well.
So, another part to that question, so does that mean that we're moving faster than another? So say there's another galaxy, we're moving faster away from them than something closer?
Mm-hmm. Okay. So like this galaxy M83, if there was a creature in that galaxy looking at the hydrogen 21 line from the Milky Way, they would see that it's shifted because it's moving away from them. Yes?
So, my question is, how do galaxy collisions happen if everything's moving away from everything?
So within a galaxy cluster, like the Milky Way and Andromeda and the Magellanic Clouds, they're all close together in space, and gravity keeps them going. But way over on the other side of the room will be another galaxy cluster. And that galaxy cluster is moving away from this galaxy cluster.
We will eventually run into...
Yeah, but within a cluster, those galaxies can collide, and exciting things happen when galaxies collide. New stars and all kinds of stuff.
Yeah, but there will not be no star collisions.
There might be.
There will be very few.
Okay, last thing, I know this group especially is excited about beautiful astrophotography, and I don't know that we're going to have time, but you can do this kind of thing with SkyNet. So Afterglow, this is an image my students made. So for the last lab, we let them collect color data, so red, green, and blue, and they learn how to combine it. And there are some cosmetic corrections, and there's some sort of 3 different levels of astrophotography processing, all built into the system. And so they were able to make really cool pictures. This is a Crab Nebula. This is Tarantula Nebula, one of my favorites. We can't see this from the northern hemisphere, so students were able to see something that they would have to go to Australia to see. M33, I think that's M33 galaxy. This image came from 1 red exposure, 1 green, and 1 blue. That's it. Yeah. But you could do 20 red, 20 green, 20 blue, and you would get a much better looking picture. But they all cost credits. That's the thing. In fact, this one too. These were all just one exposure in each color.
Wow.
And so the students get, pretty excited. They send it home to mom, and they have a great semester. And I think that's where I'm going to stop. Let's check and see if our observation is done. That would be exciting. Nope, still active. So I'm happy to entertain questions or show you more of the tools, but I know some of you may have to get out of here. So thank you for listening, and thanks for the invite, Steve.
I feel like I grew up in the dark ages.
You did.
Yeah, this is pretty sweet. I took an astronomy class in college, and the highlight was the last day. He showed us 35 millimeter slides of constellations. That was it. Yep. Yeah.
So, if a member of the Memphis Astronomical Society wanted to do something as an educational society, would we qualify for?
That would be a discussion we would have with Dr. Reichert, but he's so pro astronomy education that he might be willing to set up an account for MAS, because the Afterglow tools all come with it.
Yeah.
And I know there are people who use SkyNet without adopting the curriculum. They just create their own exercises for students.
I think the curriculum would be good for,
So I like the curriculum. Yeah, the curriculum was great for students to get the feel, but there are some things about SkyNet. It's designed for a desktop with a mouse, with a scroll wheel, and lots of screen real estate. Most students now are using little laptops with touch pads, and it was not super user friendly for that. So that's one thing I would have to update. And the labs that he designed were not right at the right level for my particular class, but that's just an educational thing. Yes?
Can SkyNet capture images of black holes?
I suppose you could get a picture of like the center of a galaxy, and there's a black hole there. I'll see if I can bring up one of their beautiful images here. I think it's under sample. I think there was one called color. Oh, this was color earlier today. I don't know what happened. Oh, I have to click on this one. The colors are not showing up. I don't know why, but it's a beautiful color image of the Eagle Nebula. It's got yellows and greens and blues. It worked in my office just fine.
Cool.
I'm not sure why that's not working.
Filter turned on.
Well, thanks for listening. I hope this got you excited about robotic telescopes. There's something called Telescope Live, I think. Some of you may have used Telescope Live Network, where amateurs can log on and talk to him, and he can tell you how to do that.
It's great, yeah. I mean, it's more pricey. It's like $25 a month to get credit.
But if you want access to really big telescopes in dark skies, that might be the solution, yeah. All right, thanks for coming. I don't know, are there any other announcements?
No, I don't have anything. I'm not sure what our program is for next month.
University of Memphis students are going to come and present something.
All right, so we'll be back here again next month.
Yes.
All right, so back here again next month, and presentations by some local university students. That'll be a lot of fun. Thank you very much for coming out, and y'all have a good evening.
Thank you.